Hello, everyone. Welcome back. We're up to lessons 17 and 18. And in these two lessons, we're going to talk about an important characteristic of a rational functions graph, and that is something called an asymptote. An asymptote is a line that gets infinitely close to the graph of a function, of a rational function, but never actually quite meets the graph. It never intersects it. It gets really, really close, but never does. And in this lesson, the first part of the lesson, we're going to talk about vertical asymptotes. And the second part, we're going to talk about horizontal asymptotes. So for vertical asymptotes, all we're going to do is we're going to take the denominator of a rational function and just take the denominator and set it equal to 0 and solve for x. Okay? Whenever we solve for x, the vertical asymptotes will be the vertical lines at those points. So with that in mind, let's take a look at the first section of examples in this lesson. So match each function with its graph without using graphing technology. Hint, find the vertical asymptote. So for this first function right here, okay, again, the step is to take the denominator. In this case, the denominator is x plus 2, and we're going to set that equal to 0 and solve for x. So if I take this and I subtract 2 from both sides, I end up with x equals negative 2. So that means this function should have a vertical asymptote at x equals negative 2. Now, if I look at these three graphs here, which one of these has a vertical asymptote at x equals negative 2? And hopefully you notice it's this center graph right here. When I look at this graph, notice if I look at the vertical line at negative 2, notice up here the graph gets really, really close to it. And down here it also gets really, really close to it. But it never actually crosses that dotted vertical line. That is what an asymptote is. So this first function goes with this graph right here. Okay. Number 2, or this middle graph, our numerator, or excuse me, our denominator is x. So if I set that equal to 0, I simply end up with x equals 0. So there's only 2 graphs left. Which one of these graphs has a vertical asymptote at x equals 0? And it's this one right here. You can see the vertical asymptote right here that gets really, really close to the graph but never actually touches it. So this one function goes with this graph. And then process of elimination says that this is going to match up with this, but let's just double check for the sake of this problem. If I take the denominator here, so x minus 2, and I set that equal to 0, I can add 2 to both sides, and I end up with x equals 2. And if I look at the remaining graph here, does this have a vertical asymptote at x equals 2? It indeed does. So the third function matches with the first graph. So that's how vertical asymptotes work. Okay. How do horizontal asymptotes work? Let's quickly go back to the lesson notes. So for horizontal asymptotes, what we're going to do is we're going to separate out the fractions and simplify. When we simplify, the constant term is going to tell me where the horizontal asymptote is. So we're going to do some more matching here. So for function a, okay, notice here the fraction is already separated out, just like this one is, just like these two are. These ones in the middle are not separated out, but this one is already separated out. So the constant term, which in this case is negative 1, is going to tell me where the horizontal asymptote is. So the question is, which one of these 4 graphs has a horizontal asymptote at -1, it looks like D does. So function A is going to match with graph D. Okay. B, same thing. These are separated out already. So my constant term is -4, which means we're going to have a horizontal asymptote at -4. So in this case, that's going to be graph B. Graph B has a horizontal asymptote at -4. Okay. C, notice the fraction is not separated out, so I'm going to separate it out first. When I do that, I end up with 1 over x, not 1 over 4, 1 over x plus 4x over x. So all I do is I just separate this out here. And if I simplify this even more, this is going to be 1 over x. And then in that second term, this x up here and this x down here are going to cancel each other out. And I end up with 1 over x plus 4. The constant term here is +4, which means it has a horizontal asymptote at +4. In this case, that's going to be graph A. Okay. D. Again, this one I have to separate out. So I'm going to do x. That's going to be equal to x over x plus 4 over x. Okay. And when I do that, x over x, anything divided by itself is equal to 1. So this is going to simplify to 1 plus 4 over x. So my constant term is 1. Which one of these graphs has a horizontal asymptote at +1? That's this one right here. So C. E, we need to separate out. So if I separate this out, that's going to be 1 over x minus 4x over x. Okay. This first one can't be simplified, so 1 over x. This one, I can cancel the x's out. So I have 1 over x minus 4. So my constant term is -4. So which one had the horizontal asymptote at -4? That was B. So function E matches with graph B. Okay. Function F. Let's separate out. So 4 over x minus x over x. Okay. If I separate that out, and if I simplify that, that's going to be 4 over x, and then minus x over x is going to be 1, just like before. So I have 4 over x minus 1. So now my constant term is -1. We're going to look for the graph that has the horizontal asymptote at -1. That looks like graph D to me. Okay. Function G is already separated. So my constant term in this case is +1. So that's going to be a horizontal asymptote at +1, which is C right here. And then lastly, separate it out already. So we have a horizontal asymptote at +4. So that's going to be graph A. Okay. So to sum up in this lesson, we learned how vertical asymptotes work. Then we learned about how horizontal asymptotes work. And that is it for this lesson.